Okay, in this particular problem, we have, let's say, a total positive charge plus Q. Let's call it 5 coulombs on located at the top on a small partial arc, and an equivalent amount of charge, say plus 5 coulombs, located on the bottom segment. And in that case, it's over a larger area, which I'm trying to draw in here. Sorry, the yellow doesn't show up. And the question is, what's the net result of these uh, two pieces of charge? And from symmetry, we'd like you to realize that the horizontal components from the top piece will cancel themselves out. So you'll have a net electric field pointing down from the top. And from the bottom, we'll have an electric field pointing up. Again, the horizontal components will cancel out. The question is, which one's bigger, or do the upward and downward electric fields exactly cancel each other out? And the answer is that the electric field due to the charge at the top is going to win out. And one way to see this is if you think about all the positive charge, if it was all located at one point right at the top, and here as you distribute it more and more along a bigger surface, there's going to be more horizontal components compared to the top, which would be all vertical. So that's sort of an exaggerated view. We can, of course, go through and do this using calculus, and maybe that's a good example because it's not an impossible calculation to do. So there is the explanation with the qualitative, but go ahead and set up this calculation. Right, so we're going to integrate a bunch of small charge segments, say for the top arch here, a little bit of dq, and all we really care about is the vertical component. The horizontal component's going to cancel. So you can see if we want the vertical component there, we're going to take the total value times the cosine of theta will give us the vertical component of the electric field, and then it's 1 over 4 pi epsilon naught r squared. That's kq over r squared. And the cosine theta is just to give the y component. So we can rewrite this dq in terms of lambda, charge per unit length, times the length, and then we can rewrite the integral this way. And so that all we're really integrating over here, r d theta, that's the length of our sample, and then the cosine theta here is going to be, again, just giving us the vertical component. And I pulled all the constant things outside of the integral. And if we go ahead and do that, we can see that doing the integral, the vertical component of the electric field goes as sine of theta top, so that's how wide, that's the maximum angle, how far it's spread out, divided by theta top. And I just did a plot here, and you can see that the more it's spread out, here we're going out to angles of 1.4, then the weaker, the less the vertical component is of the electric field. So the calculus matches what we expected.